Hey everyone, welcome. दोस्तों आज हम इस यूनिवर्स के सबसे बड़े और सबसे दिलचस्प रहस्यों में से एक पर चर्चा करेंगे. I'm talking about a secret hidden deep inside the atom. We're gonna completely unravel the mystery of the missing mass, or as we say, missing mass का रहस्य. आज के इस डीप डाइव में हम elaborate करेंगे कि exactly how the building blocks of our universe are held together. Like, where does the incredible power of stars and nuclear reactors actually come from? Let's dive right in.
Okay, so imagine you've got a box of Lego pieces. You put them all on a weighing scale, and let's say they weigh exactly 100 grams, right? Now, you take those pieces and build a really cool little toy car, but when you put that finished car back on the scale, it suddenly weighs only 99 grams. अगर हम parts को जोड़ें, तो total mass कम क्यों हो जाता है? If we add all the parts together, why does the combined mass actually decrease? कहाँ गया ये mass? It sounds like magic, right? But this isn't just some crazy thought experiment. This is literally happening inside every single atom in your body right now. Let's find out why.
Here's our roadmap for today. We'll cover the mystery of the missing mass, Einstein and binding energy, the magic of the curve, fission and splitting heavy atoms, and finally, fusion, the power of the sun. Let's get to it.
Section 1. The Mystery of the Missing Mass.
So, let's start at the absolute foundation of matter. We're looking at tiny nucleons, protons and neutrons. जब ये protons और neutrons combine होते हैं एक nucleus बनाने के लिए, तो कुछ mass अचानक गायब हो जाता है. It's wild. The mass of the complete nucleus is always, and I mean always, less than the sum of its individual parts. We call this phenomenon the mass defect, represented by the symbol delta M. अब सबसे बड़ा सवाल ये है कि ये मिसिंग मास करता क्या है? Well, it is directly responsible for nuclear binding energy. Think about it. Protons have a positive charge, which means they violently repel each other. To keep them packed so tightly inside the nucleus, you need an unbelievably strong glue. That missing mass, it's literally the energy acting as that glue to hold the whole thing together.
Moving on to Section 2. Einstein and binding energy.
To truly grasp where that missing mass goes and how it transforms into this cosmic glue, we have to talk about Albert Einstein. You've all seen the most famous equation in the world, E equals mc squared. Well, Einstein's theory of special relativity tells us that mass and energy are essentially just two sides of the very same coin. Mass-energy equivalence का सीधा सा मतलब है कि mass को energy में और energy को mass में बदला जा सकता है. So, that missing mass, it hasn't just vanished into thin air. No way. It's been converted entirely into the binding energy that locks the atom together.
And you won't believe how much power is locked inside matter. सिर्फ एक atomic mass unit, just 1 AMU, का mass defect होने पर एक massive 931 mega electron volts की binding energy release होती है. Just a tiny microscopic loss in mass creates an absolutely staggering amount of energy. ये energy इतनी ज़्यादा है कि our ordinary chemical bonds, like fire or traditional explosives, they literally look like nothing compared to this.
All right, Section 3. The magic of the curve.
Now we're going to zoom out a bit. Instead of just looking at one single atom, let's see how this binding energy applies across the entire universe. यहाँ हम binding energy per nucleon को mass number की against plot को ran. Notice how the curve shoots up rapidly for light elements, hits this plateau, and then slowly drops off for the heavier ones. But look right at the very peak, the absolute highest point. That is iron 56. Iron 56 is literally the most stable and efficiently bound nucleus in nature. It's like the gold standard of the universe. Every single element essentially wants to be as stable as iron.
Now, before we analyze the two sides of that curve, I've got to point out a super fascinating quirk in nuclear physics. Scientists notice that certain elements are just exceptionally stable and abundant. Kyun? Because they possess what we call magic numbers of protons or neutrons, specifically 2, 8, 20, 50, 82, or 126. Jase calcium, it has exactly 20 protons. These magic numbers correspond to completely filled nuclear shells. It's actually really similar to how noble gases have completely filled electron shells, which makes them highly stable.
And if you like numbers, this data table literally proves the math behind that curve we just saw. Just look over at the right column, the binding energy per nucleon. A really light element, like deuterium, has a low value of about 1.12 MeV. Then look at heavy uranium, way down at 7.57 MeV. But check out iron 56, sitting beautifully right in the middle at 8.79 MeV. Iron has the highest binding energy per nucleon. That means its nucleons are packed together the tightest, with the maximum possible amount of mass transformed into binding energy. Which brings us to Section 4, fission, or splitting heavy atoms.
Since we know iron is the ultimate goal of stability, what exactly happens to those really heavy, unstable elements on the right side of the curve? Well, incredibly heavy elements like uranium face a huge problem. उनके अंदर इतने सारे पॉजिटिव प्रोटॉन्स होते हैं कि उनका इलेक्ट्रोस्टैटिक रिपल्शन न्यूक्लियर फोर्स पर हावी होने लगता है. The protons literally want to rip the atom apart. So, to reach that stable peak, these heavy elements undergo fission. They split apart into smaller, more stable fragments, moving leftward down the curve toward that valley of stability. And the crazy part? When they split, they release all that excess binding energy.
But fission isn't just some random splitting event. Let's actually trace the steps here. When a large nucleus, say uranium-235, absorbs a stray neutron, it briefly becomes uranium-236. ये U-236 इतना unstable होता है कि ये तुरंत दो छोटे न्यूक्लियाई में टूट जाता है, like barium and krypton for example. But here is the critical part, the real game changer. This split releases a massive amount of energy and it ejects more free neutrons. Those new neutrons then fly out and hit other uranium atoms, causing them to split, which releases even more energy and more neutrons. एक single event, एक massive chain reaction बन जाता है. And you know what? This is exactly the science that powers our nuclear power plants to generate electricity. And yeah, it's also the science behind nuclear weapons.
Finally, Section 5, Fusion, the power of the sun.
So, that's the story on the heavy side of the curve. But what about the light elements? To understand this properly, let's quickly contrast the two. Fission was all about breaking heavy things apart, right? Well, fusion is the exact opposite. Nuclear fusion is the fusing together of two small light nuclei to produce a much larger nucleus. ये process light elements के साथ होता है, जैसे hydrogen. If you combine light elements, you move rightwards up the curve towards iron, and man, the process releases a staggering amount of energy. In fact, fusion releases way more energy per nucleon than fission ever could.
But of course, there's a huge catch. Fusion is incredibly, unbelievably difficult to achieve. क्यों? Because you are trying to smash two positively charged atomic nuclei together. And as we know, like charges fiercely repel each other. That's electrostatic repulsion. उनको पास लाने के लिए और चिपकाने के लिए आपको extreme pressure और करोड़ों डिग्री का temperature चाहिए. Literally millions of degrees. Under normal conditions, they're just gonna bounce off each other. These extreme conditions are naturally found in only one place, right in the core of a star just like our sun. The immense gravity of the sun provides the crushing pressure, and the intense heat allows those hydrogen nuclei to literally slam together and fuse into helium.
So the crucial point we keep coming back to is iron. Stars essentially spend their entire lives fusing lighter elements into heavier ones, and that released energy is what keeps the star shining. Hydrogen becomes helium, helium becomes carbon, all the way up the chain to iron. But once the star creates iron in its core, the party is completely over. Iron's incredible stability means that fusing it further actually consumes energy instead of releasing it. Binnen extra energy K, the star can't fight its own crushing gravity anymore. And that sudden collapse, it leads to massive, universe-shaking supernova explosions.
This whole journey through missing mass and binding energy leaves us with a totally mind-bending question about the far, far future of our cosmos. Think about it. Since every element on the curve naturally wants to reach the absolute stability of the iron nucleus, either by splitting down via fission or building up via fusion, क्या universe का end सिर्फ iron बनकर रह जाएगा? Trillions and trillions of years from now, will the entire universe just be cold, dark, stable balls of iron? It is a wild, fascinating thought to leave you with today. आज के session में जुड़ने के लिए शुक्रिया. Thanks for exploring with us. Keep looking up and always keep questioning the universe.